Hello, Year 12, Western Australia, and welcome back for instalment 3 in our Mathematics Applications Exam Preparation course for the WACE. Tonight's session, sequences recursion and growth and decay. The Jodstar is back. He'll be working you harder than ever. Can you please get ready to type into your question and answer panel and send responses and questions to all panelists, please. You'll be not only sending questions, but you're going to be asked to be sending a lot of answers as well. You know number sequences, you know arithmetic sequences, you know geometric sequences. What comes next? What comes next, I can tell you, is Jodstar. You there, Jodstar?
Yes, I am. Thank you very much for the welcome.
Let's swing into it. I shall transfer across to you.
Wonderful. I'm just looking to get my screen up. Well, it's been a busy week for me. Year 12's has just about finished the content, and we're looking forward to, well, I'm looking forward to getting prepared for the school-based exams, and then we've got the WACE exams, the beloved ATAR. So, in this session...
Do I need an ATAR?
Be wonderful.
Yeah.
At sequences, recursion, growth and decay. Presenter, me, Mr. Jody Crothers, also known as Jodstar at times. Now, what I want you to do is I've got 3 questions coming up here, 2 straightforward ones, and a third one I'm looking forward to some of the answers. So, I'd like you to, in the chat or the Q&A, enter the 3 numbers, which will be the answers to these 3 questions. What number comes next? I'll let Brian take a look. Hopefully we'll get a few answers through. Any luck, Brian? We're getting a few responses.
I reckon I know the answers. No, we're fairly slow on responses. Are they still asleep in Western Australia, mate?
Oh, it's sunning up today. We've had a couple of wild weather days. Roofs off buildings. The gate at my house came apart 2 days ago.
Wow.
I'm putting it back together.
Wow. No, it's been sunny and lovely here. I was out on the mower yesterday.
Oh, not looking forward to that. Okay, well, tune this for answers, and if there's not, it's okay too.
I will continue watching for them, mate. I'll let you know.
The first one's pretty straightforward. 2, 4, 8, 16. There's a common ratio. We're multiplying by 2. It's a geometric sequence. The next one would be 32. Second one, 100, 87, 74. No common ratio there. There is a common difference. It's arithmetic. We're subtracting 13 each time. Next one, 61 by my calculations. Now the third one's really more important to me. It's quite challenging. If we have a look, it's 11, 14, 14, 6, 11, 7, 3, 4, 1, 16. Quite a complex pattern. Now, I'm hoping for the next one to be 3 or 4, but the reality is we're not sure what the next number in the sequence, as they're the finishing positions of the Fremantle Dockers in the past, 11 seasons, 10 seasons. So we're hoping for a lower number next time. So, let's hit the content. SCARSA puts out a really clear syllabus for your teachers to follow, and the textbooks you use are designed to cover this content, along with additional top-up from your teachers. Today we're looking at the sequences part. Topic 3.2, which is growth and decay in sequences. Nominally they said 15 hours depending on how many hours you have a week, that's 3.5 weeks worth of coverage, plus or minus excursions, assemblies, and the like. We're going to look at recursion to generate an arithmetic sequence. We're going to display terms of arithmetic sequence in table and graphical form, so we'll go through that. And we'll demonstrate how we can use them to model linear growth and decay in discrete situations. We're also going to look at coming up with a rule for the nth term, so not written recursively, but T at n equals something that involves just n's, not terms before or terms afterwards. And we'll also look at using arithmetic sequences to model and analyse practical situations involving linear growth or decay. And the main one is not overly practical, the example we're going to use, but it is an example of the sort of practical things you may get in the exam. Alongside this, we look at the geometric. We're going to use recursion to do that. We're going to look at the table graphical for geometric. We're going to go through rules for the nth term again. And we'll look at some situations to model and analyse numerically and or graphically geometric growth and decay. And the last one are called sequences generated by first-order linear recurrence relations. The reality is, as we cover the first two, we will be using first-order linear relationships to generate those terms and display in tables and graphical. We'll generate sequences, and we'll use those sequences to model and analyse practical problems. Now, your SCARSA handbook, and the SCARSA formula page, has this information. This is what relates to what we're covering today. This you'll have in both the calculator and the non-calculator section. It's got T at 1 equals A. So the first term is referred to as A. The subsequent term is T at n plus 1 is equal to B lots of Tn plus C. B being the common ratio in there, and C being an amount being added on. But when there is a C, the B is not a common ratio, it's just a multiplying factor for the term before. And we're looking at terms of n greater than or equal to 1. So we're not looking at T zeros or negative terms, we're looking at greater than or equal to 1. Now, first came off the rank, the arithmetic sequence. Simply, first term, write it in terms of T and n, is equal to A, which is the first term, plus n take 1, lots of the difference. There's a common difference, and it generates a linear graph, which we're just about to do. And here we go. Here's our first one. 7, 11, 15, 19. As we can see, we're adding on 4 each time, and T at 1, the first term, is 7. Now we're going to move to using our handheld to do this. And there's a number of ways we can do this with our handheld. One way I like is using a graphing page. So if you're starting from scratch and your new document, don't want to save that, I'm going to choose a graph page. We can go menu, graph, entry and edit, and here we are, sequence. And we're looking at the sequence version, 1, 7, then 1. This gives us a sequence which is U1 at n, which replaces U1 is the same as T. We're using n, so the term before it will be n take 1. So the term before it is U at 1, n take 1, so that's the term before, plus 4. And we've already established that. Our initial term in this sequence is 7. And if we want, we can go down and we get at how many things we do. Let's just do 10. And then we hit enter. Oh, can't see anything. Well, our first term should be 7. our graph only goes up to 6.63. So we can try menu, window zoom. I always like trying fit first. Look, worked first time, which is nice. We've got half of our recursive equation. Remembering that when you have a recursive equation, you've got two parts. You've got the equation and you've got a term that's defined, usually the first term. In this case, T1 down here is the initial term, and it tells us. And we can even find out, by the equations, our initial term is 1, 7. So 7 was the first number in there. So this has given us a little function that will help generate a graph of our arithmetic equation. But the other thing we need to be able to do is show it in tables form. So if we go Control-I, it'll insert a new page. This time we want a list and spreadsheets page. And this is the traditional way you see your list and spreadsheets page. But one thing you may or may not have used, we go Menu, Table, we can actually switch it to what they call a table view. There, we can actually go through and select our function, which in this case is U at 1. What it means is like our sequence setup. It came up with a syntax error, but it produced it anyway, so I'm not quite sure why the error appeared there. So I'll make this a bit bigger so we can see. So C, we can see 7, 11, 15. So we can actually go down and see the terms it's generating, which is nice. And while we don't use terms of n less than 1, it doesn't like it either, which is good, because we're not using those ones either. So we've got that as a table, and we've got it as a graph, so we can see what's happening. If we go tab back here and we go change it, instead we want to have it take 2 each time. Menu, window zoom, let's fit it again. So it's going downwards, as you would expect. We can flick across to our table, and we can see what's happening to the values as we drop by 2 each time. So this is giving us a chance to have a look and see what the arithmetic progression or arithmetic sequence looks like. You will get questions at times which ask you, is this a graph of an arithmetic or a geometric? And you'll need to look at the starting point, where the values are going. Is it a straight line? Most likely the arithmetic. Is it a curve? You'll need to have a look what sort of curve it is. Is it an exponential function? So we've got some values. We can change our equation like that. Now, what I'm going to do now is I'm going to start a new document. I like new documents. And do the same thing for a geometric. So the geometric sequence we're going to look at will be this one here. 2, 6, 18, 64. What I'd like you to do now is go to the graph page, press menu, graph edit entry, sequence, then sequence, and type in the function of the equation. So go through, put the recursive relationship in there, and see how we go. I'll give you a couple of minutes to do that. Once you've done that, if you can go to the Q&A or the chat and put formula entered, that would be great.
Yeah, that would be good. Last week we got people eagerly typing into the chat. A bit quiet tonight, though.
Must be so enthralling. I'm going to put those in while I'm waiting.
Righto.
going to do 5 terms this time. Otherwise, I'm a bit scared to get a bit fast. And here we do, we've got 2. I'll try again to fit it. And there we have our plot of that recursive formula.
Beautiful.
Control I again will bring up a list and spreadsheets. List to table mode. We'll choose the same one. And we'll go through and we'll have a look at the values. I'm glad I didn't go more than about 5, which is 160. If I'd gone to 10, I'd be up to 39,000, which wouldn't be a pleasant. Again, the ones before, it doesn't like. Which is fine. Okay, so we've got a set of numbers. We've come up with a recursive formula. We can enter that and graph it. We can enter that into a table. What we have to look now at some of the algebraic things we can do with them. So I'll go back into this one. I'll go back to our original function here. I'm just going to go back up to this slide here. As you can see, we've got a recursive formula, t at n plus 1 is equal to t at n plus 4, first term being t1 equals 7. If we want to write that as an nth term, we know that the starting value is 7. The common difference is 4. So we can write that as 7 plus n take 1 lots of 4. That's perfect. If we want to take it a little bit further and simplify that, we can expand that out, giving us 7 plus 4n take 4. That simplifies down to be 3 plus 4n. Whereas our sequence before was very discrete with the values, n plodding along, we can actually use 3 plus 4n and graph it. So if we go back here, we can go menu, graph edit entry, we can graph a function, and so it'll be 3 plus, in this case we're using x's, 4x. And that's giving us the knowledge that our algebra, rewriting the formula in terms of t at n, gives exactly the same values as our recursive formula, which can be very useful just to check that you're on the right track.
Yeah.
Now we can do the same thing with the geometric. So let's go have a look at the geometric. The general term t at n is equal to a at r to the power of n take 1 make that a little bit bigger. So we've got 2 times 3 at n take 1 to the power of n take 1, which is great. We could use that and graph that, and that would graph just fine. Or we can simplify it out, which gives you 2/3 3 to the n, which in some ways isn't that much simpler. So sometimes using this version here will actually be easier. So what we're going to do is I'm going to graph that and see if we've got our algebra right. Menu, graph edit entry, a function again, and I'm going to use 2 times 3 to the power of x take 1. Wishing me good luck. This. Oh, wonderful. I'm not too bad.
Looks good.
So we've now got a function, and we've got a recursive relationship with an initial term, and they all match up. We could also get the data done as a table. Now from there, with these skills, it allows us to go on and solve some of the problems associated. So let's have a look at those. It'll be wonderful to do a question that sort of simple in the exam, but we probably won't. The other thing we can do in our list and spreadsheets is we can generate a recursive using the sequence generator. And we'll have a look at that after we've gone through and solved some of these questions. Now, the first question we're going to get you to answer is about wombats. A population of wombats growing according to law, P equals 32 times 1.05 T. Find the population in 10 years' time, and how many years will the population be expected to reach 40. I'm going to give you a couple of minutes to plug in some values, then I'm going to work through, and we can see how we compare. If you've got an answer, type it up, put it in, and we've got it on record then.
Let's see who's first.
Moments like this, I wish I had prizes to give away.
Oh, don't we have prizes? I thought we did.
It would be lovely.
Is it laptop computers and things? Oh, look, I don't know.
Happy to give your laptop away?
Yeah, I've got plenty of old ones.
Okay, Evie, I'm going to assume we've got some answers through because I think that's a positive thing to do. Thank you to those people who have answered. People who haven't, give it a go next time. Everyone doesn't have to know, but it's good to actually engage. Moving your memories and your thoughts and your understanding from your short-term to your medium-term memory really improves when you actually do a bit of work to go with it. So here we've got, I'll move it across. Lovely question. Population of wombats. And there's a formula for that. So I'm going to define that formula, P at T, then control colon equals, or little duck, as some people like to call it. And that's equal to 32 times 1.05 to the power T, which is what we're using. So we've defined our formula there. We're trying to find out the population in 10 years' time. So the population in 1 year's time, we multiply 1.05 once. So in 10 years' time, it will be P at 10. We hit enter. And we've got 52.1246 wombats. And that's great. How would we answer that?
Well, like wombats.
Yep, those 0.12 wombats, they're the dangerous ones.
Yep.
We're going to ignore them. So, in fact, we're going to have 52 wombats at that stage. It's really hard to have part of a wombat, and they're pretty messy.
Could be messy, yep.
The next part is we want to know in how many years will the population be expected to reach 40. And that's good. We can keep on table, plough through the values. But we want to know, we want to solve the problem when P at T is equal to 40. So when that equation was equal to 40, we want to know what value T will be. So we'll enter that. So that's telling us 4.5734 thing the time. So it's asking how many years. So at year 4, we're going to have less than 40. And at year 5, we're going to have more than 40. In how many years? In 4 years it won't have. By 5 years, it will have reached 40 and actually exceeded it. So my answer to that would be 5 years, it will have exceeded 40.
Yep. And that's an important one, isn't it? To make sure that you actually answer the question in the context that it's asked. So students do need to watch out for that one.
Wonderful. Now, I'm actually going to hand you over now to Brian, who's got another question to work through. And then I'm going to bring you back at the end to go through a combined question, which uses arithmetic and geometric and ladders.
Ladders? Any snakes? Snakes and ladders?
But there are giants.
Okay. So here we are, another exam question. And I've added a bit extra into here. I'll just leave that bit off to the side at the moment. The original part of this question, paper's written by Australian Math Software, as you see, and students really at this stage of the year, your very, very best preparation, apart from watching our webinars, of course, is to be practicing exam questions. That's the thing. Watching the webinars, you get our words of wisdom, and you also get exam questions, such as this. So in this one, we have a story of a lake which is contaminated with deadly weed. That's not good. So we're going to spray it. Now, before we commence spraying, the weed covers 100 square metres of the lake. And the poison is not too bad, because what it does is it kills off about 40% of remaining weed each day. And if you just ignore my little yellow additive here, because that was my extension of the problem, I'll leave that to the side. So the original question from Australian Math Software was determine the coverage of the weed after the spray has been applied for 1 day, and then for 2 days, and then for 4 days. And then the question is turned around the other way, as you see in part B. How many days? So this is using that solve type command that Jody just showed you. Turning it around backwards, how many days will there be only 8 metres or 8 square metres? I'm going to interpret that as being less than or equal to 8 square metres of weed left on the lake. Now I'm going to set things up slightly differently from what Jody showed you. First of all, to get these sequences going, just on the calculator page, the easiest of the lot, we started with 100 square metres. If I type on a calculator page 100 and press enter, then if I start with a command on the next line with an operation, I'm going to multiply. As soon as I press the multiplication sign, the calculator on the command line has returned ANS, which means previous answer. So previous answer. Now, a little bit of quick arithmetic here. If the spray killed 40% of the weed, what percentage remains? Yes, those of you that said 60 have got that absolutely correct. So if I multiply the previous answer by 60%, in other words, 0.660 if you wish, then I will have what remains. Okay, 40% gone, 60% remaining. But the beauty is, once that's set up, every time I press enter, it will subsequently repeat that recursive operation. And this one, of course, is a geometric sequence. What is happening is we're taking the previous term and we're multiplying by 0.6 every time. So what you see now is the amount of weed left after 2 days. The question, if you remember, was how much after 1 day? Those of you who said 60 square metres got that correct. How much after 2 days? 36 square metres. If I press enter again, I have 21.6 square metres remaining after 3 days. And if I press enter again, this is answering the part of the question, how much remains after 4 days? Now, how many days before I'm under 8 square metres? Well, I'm at 4 days already. Press enter again. Well, on the 5th day, by the end of the 5th day, we're under 8 square metres. So that can be a simple way of answering these. To go further, if the sequences were longer, then certainly it's much better off defining it as a function and either putting values into the function like PT or P10, as Jody just showed you, and turning it around the other way, doing the solve PT equals 40, or PT is less than or equal to 40, or less than or equal to 8, as it was in this case. I'm just going to show you I'm going to show you 2 other ways to do this very same thing. In a lists and spreadsheets page, I could say weed, and there'd be 100 square metres. Hang on, 100 square metres on the first day. And then you could do this in Excel as well, on a spreadsheet. And interestingly, the data, if you have data lists from Excel, you can directly transfer between Excel and Inspire. That is very, very useful. If you, for example, are looking at, well, last week we looked at some data for our data analysis. If you are taking a data set from, for example, the Australian Bureau of Statistics, so it might be census in schools data, you can download that as an Excel spreadsheet, and you can copy directly from that into this TI Inspire software, or TNS. So what I'm going to put in this cell, I'm going to start with equals. So that's a formula in a spreadsheet. So it's going to equal the previous cell multiplied by 0.6, you will recall. So in other words, 40% of the wheat is gone. So there's our result. Now, what I'm now going to do is take this, and I grab from this here, and I'll just grab the corner of that cell and drag it down. What happens is that the cell is copied in a relative way, it's referred to. So here I have A1 multiplied by 0.6, and the cell below it says A2 multiplied by 0.6, and so on. And I could have dragged that further. I only dragged it down 5 cells. Okay. Now, another way I could have done that is I could have just generated a sequence using the command, again, that Jody showed you. So I place the cursor into an empty cell here, top of this column, menu, data. This is just so useful, this one. Generate sequence. And it took me a while to work this one out initially. UN, what I now need to make to generate this sequence, and this is a difference equation. It's called a difference equation because we're developing the next term based upon the previous term. So the bracket N here means the nth term. Which term am I up to? Well, I'm going to define my nth term by looking at the n minus 1th term. I'm not sure if that's correct English. My wife's an English teacher. She's listening and she'll probably correct me on this afterwards. But UN minus 1, I'm calling that the n minus 1th term, which you know has to be multiplied by 0.6. Now that's the way this is set up. Initially when I looked at this syntax, I thought, I need to expand this. And I had UN minus U, but no, it's nothing like that at all. That's incorrect and silly. The first term, initial term, was 100. That was the amount of weed that was on the lake initially. I can ignore this one, and Nmax is just how much we're going to go up. Look, let's generate a dozen terms, or we could do more. It's going to step them up one at a time, and let's just hit go. And there it is. So this time you see I've got more than just those 5 terms. It will develop a list of a dozen terms for me. So that's what's happening. So our weed is disappearing. Now that's a geometric sequence. If we had a different situation where rather than, say, 40% of the weed being killed off each day, but let's say we bring someone in to do a bit of weeding, and this person is dragging the weed out by hand and does, well, I've been conservative here, 3 square metres of weed per day pulled out by hand. That would be an arithmetic progression, because what would happen is that the weed would go down by 3 metres per day every day. If we use the hand weeding plus the poison, then we've got what I call a hybrid situation. In fact, it's a linear recursive difference equation. So because it's part multiplication and part arithmetic, I'm just going to quickly show you that situation in the calculator, and I'll hand you back to the JodStar. I'll call this weed 2, and to do that data command again, the difference would be that in the generating sequence, I'd have my 0.6 multiplied by that, UN minus 1, subtract 3. And listen, guys, I'm going to make a personal confession here. This stuff is just fantastically useful, and I actually learnt it not from my own research, but from my own students when I was teaching this topic to my Year 12 class, and they got onto the calculators and they're forever researching, and they read the manuals, they look at YouTube, and they find all these clever ideas. And so I actually learned how to do this from my students, which I think is a good message for teachers, really. Don't be embarrassed to learn from your students, because they're often very, very clever. So you can see here I've got a hybrid situation, part multiplication, part subtraction, and so here would be the new sequence. Do you like that, Jody? Negative weed? That's an interesting situation. We've got rid of all the weed at that point, which is great. I'm going to hand back to you, mate. You're ready to have a go. Jody, are you there? He is indeed. How you going, Jody?
Doing well, just waiting for that magic ball to transfer across.
That magic ball to come back. It's all back to you, mate.
It is. Wonderful. Now, the last question we're going to look at combines arithmetic and geometric. It's definitely one of those real-life situations. Maybe not. Okay.
Speaking of which, and I'm just going to cue you on this, the maths humorist, we haven't heard the humour side yet.
Oh.
Apart from some rather funny sort of questions.
I've got a wonderful recursive joke.
Recursive joke?
Yes. Pete and Repeat are sitting on the bench. Pete gets up. Who's left?
Repeat.
Pete and Repeat are sitting on a bench. Pete gets up. Who's left?
Oh, yeah, okay. You've got me. Repeat.
Good. Okay.
Okay. We'll see if that gets edited out or not.
We've got a wonderful character called Jack. I know, it's amazing. And Jack's got a ladder, and his ladder's length can be defined using the formula L at n is equal to L at n take 1 plus 20. L at 1 equals 50. N being the number of rungs. One night, I'll even put that, N being the number of rungs. One night, Jack goes out in the town, has a big night, trades in his family cow for some magic beans. Old story, heard it before. So he plants the beans at 6 p.m. one night and waits to see his incredible beanstalk the next morning at 5 a.m. Now, the beanstalk height in centimetres is given by the formula B at T is equal to 1 times 30 T take 1, with T being the number of hours from the time of planting. So that's our scenario. He's got a ladder, with N being the number of rungs, and we've got a beanstalk that's growing. How tall was the plant when Jack woke up in the morning? Okay. Here's where we hit our calculator. Move that across, make the calculator a little bit bigger, which is useful. Screen bigger. There we go. Menu. I'll hit the home button. New document. No, I don't want to say what I was doing before. I'm going for a calculator. So we'll go back a step. Jack's plant. Jack's plant, we can define B at T. It's the beanstalk at time, colon equals, or control little duck, 1 times 30 times 30 to the power of T, take 1. So there's our beanstalk formula. We'll go back. We'll have a look at the next part. So we want to know how tall the plant was when Jack woke up in the morning. He planted it at 6, woke up at 5. So I'm thinking that's 11 units of time. 11 hours have gone by. So the beanstalk at 11. Whoa! That's really big. Does that seem realistic?
Well, it would reach above the clouds.
I think so. Really interesting. And not what I had before, which is what really is making me ponder. So how high is this beanstalk? Centimetres. So if we divide it by 100.
Still big.
Still big. So that's metres. Divide it by 1,000. That's huge.
Still big.
Still big. Still
Kilometres.
big.
How many kilometres to the moon?
Yes. That's crazy. Crazy big. I think I've made a mistake in my question, which is quite interesting. It's supposed to be 1.3 there. That might be a better answer. So I'm going to go back and redefine B. Somewhere in my typing.
1.3.
That's better. He's got a tiny one after 11 hours. 1.3.
Yeah.
Centimetres. This isn't much of a
How about centimetres, remember?
Yeah, 13 centimetres. It's tiny. Absolutely tiny. So he's not particularly worried. These aren't very magic beans. And his ladder at this stage, not a problem. So, Jack waits a month. So he goes out a month later. We'll make it 4 weeks. So 28, lots of 24 hours. It would be huge.
Oh, okay. Now it is big.
That would be big. So it's gone miles by then.
The E bit stands for enormous.
Enormous times 10 to the power of 76.
Mm.
I'm going to go switch over to file I prepared earlier and see what it actually is telling me. Here. Oh, here's where my typing error went. Bean tree actually is a rate of 2.3.
Ah.
There. This will give us a better one. Now I'm embarrassed. So, here we go. Third time lucky. Done. B at 11. That's a lot of centimetres. We divide that by 100. 41 metres. That's fine. So, after 11 hours, on this new improved bean formula, third lot of beans, it's gone 4,142 centimetres. Next we need to do is write down the length of the ladder in terms of N. So at the moment we've got a recursive definition for the ladder, but we want one that will be in terms of N, so no recursion. So L of N, the length of the ladder, is going to be equal to A, the first one, plus N, take 1, lots of the difference. And the difference was 20. So this ladder, 50 centimetre gap up, and then every rung you add on, you're adding another 20 centimetres to go up. So there we have the formula, as we write down for the answer. the ladder length, which is a linear formula, written as the nth term. Now, how many rungs would Jack need to get up to the 41 metres? So we want to know, we want to solve the question.
Yep.
L at n is going to be equal to 4142.65. We want to know that answer in terms of n. So this is telling me 205 rungs would leave him just short. So the answer would be 206 rung ladder. He's going to have to get on and keep building fast to get the top of his beanstalk. Oh. Now Jack's doing well. Jack gets his ladder, got 1,000 rungs on it. Builds it very quickly. Jack's a very good ladder builder. 1,000 rungs. How high is that going to be? Oh, 20,000 centimetres. So about 200 metres. For how long is this ladder going to be useful? Well, let's find out. What's going to be the value of V? We want to solve when B, the height of the beanstalk, B at n, is going to be equal to the answer we just generated there in n. So this is going to tell us how many hours. Wow, not going to last too long. 12. So let's go back. How long will the ladder? So after 12.8, it'll be fine. 13, the ladder is going to be too short. So it's only going to last for 12 hours. Important to read the question so you know which one you're answering. Great. Now this beanstalk keeps on growing up. There's a giant castle which is 2 kilometres above Jack's house.
Bring some sorry. Sorry, Gabe.
Okay. How long is it going to take to get there? Well, I'm going to go solve again for B at n. And it's going to be equal to 2 kilometres. Well, that's 2 kilometres, but that would be 2,000 metres. But I think it's centimetres.
Yep.
And units matter. Because if you don't get the units right, you're not going to get the answer right. Oh, wow. So 15 and a half, just over 15 and a half. So 16 hours. You'll be able to, it'll be up to, 16 hours is going to be up to the Giant's Castle. That's good.
Then I get my fee fi fo fum, is that right?
Then you get your fee fi fo fum.
Yes. Excellent, excellent.
Now the last part here is each of the rungs on Jack's ladder is 40 centimetres in length. What distance of wood be required to build the ladder? Now here's a ladder. So if we want to build a ladder to go 2 kilometres tall, we're going to have 2 kilometres on one side plus, times 2. So the rails are going to be 400,000 centimetres worth. Now the rungs, we're going to work out how many rungs are going to be. That's rungs are the number of n. So we need to find out how many rungs are going to be for this one. So we're going to solve the ladder equation when that's equal to the same value, 2 kilometres.
There we go. On that half a rung, yep.
Yep. Whoa. Half a rung's really not quite useful, is it? So we
I reckon, look, hang the expense. After all that, just go another half rung.
Yep, so we're going to say there's 9,999 rungs. And each of those rungs is 40 centimetres. So that's our length of rungs. We combine our length of rungs
with the value up the top.
Rails. And that tells you how many centimetres of wood's required.
About 7,000 metres of wood.
Yep, so we'll divide that by 100. Oops, we'll divide over here rather than the PowerPoint. Control Enter. And do that
that's double. That's that answer thing again.
Yes, so I'll grab the
I've been caught on that. You are not Robinson Crusoe on that, don't worry.
Control C.
Yep.
Control V. Control Enter. So that's our answer. That's not our answer. Our answer is all the way up here. Is it not?
If it was in centimetres, yes. Control
C. Control V. And I know that is going to be, that is the correct answer, 7,999.6 metres. And if I was building it, I'd probably go 8,000.
Yeah.
I'd probably go 810. But the length required, everything being precise, 7,999.6 metres worth of wood. But what answer would we give? We actually wouldn't give the answer in metres because it's not asking for it in terms of metres. We're going to go back and we're going to use this value here
use that one.
Because they're talking in centimetres. We can do that in terms of centimetres in this question. It was in terms of kilometres. It would be about 8 kilometres worth of wood. So by defining the functions, L at N and B at N, I can do a whole variety of functions. So recursive's great, but if you can convert it into a form, the nth term for each of them, you can make them interact more easily.
So, Jody, you'd have to use some of those carry forests that you got down south there.
Yes.
I've been to them. I have visited.
They're gorgeous down that way. The Gloucester Tree down in Pemberton's wonderful. You can climb that.
That's the one. Yep.
You got the Valley of the Giants. You can actually do the treetop walk these days. So, guys,
fantastic.
Quickly go back to the start. We've looked at sequences. We've looked at arithmetic. We've generated an arithmetic sequence. We've done it in a table. We've done it in a graph. We've converted it to nth term. We've done the same for geometric. We've had a look at the first order linear relationships that Brian went through. Remembering that, we've got the formula there for the first order. So you're multiplying by something and adding something. So this should give you the skills you need to be able to go through and answer the exam questions as they appear in your school-based exams, which will be coming up, and then again in the WACE exams in November. Thanks very much. Do we have any questions come through, Brian, that anyone wants answered?
I've been watching. I've been watching keenly, but no, it's been very quiet tonight, Jody.
Oh, that's fine.
Yep. I thought we might have copped a bit of cheek from that PF fellow, but even he has been quiet, which that is a surprise. One for the books. So, trust you've got some really useful stuff out of this evening's or this afternoon's webinar. I think, as Jody just explained, that was just a great overview of what is a very important topic and is definitely going to be featuring in your exam this year. Join us again next week, please, where we return to the data topic, and in particular, an area that I know is of particular concern to students. We'll be looking at the time series, particularly smoothing and deseasonalising of data. So we'll be looking at those seasonal indices where we adjust data for to make allowance for the seasons. You are going to get exam questions on that, so it's well worth tuning in. So until then, I bid you well and happy studying, and we will see you again same time, same place next week. Thanks, Jody.
No worries, Brian. Thank you very much, and see you all next week.
Catch you then.
Bye.